Hello, my name is Gal from the Hebrew University of Jerusalem, and this is a talk about the approximate degree of bipartite perfect matching. In today's talk, we're going to be considering bipartite graphs that have two n vertices on each side. And we're looking for a perfect matching, that is, a subset of the edges, such that every vertex is incident to exactly one edge. In Edmond's seminal paper, he devised an efficient algorithm to find the maximum matching in a bipartite graph. Since then, many efficient matching algorithms were constructed. For today, we're only going to be discussing the deterministic dense regime, where the number of edges is proportional to n squared. So this is a very rough plot of the progress made in this regime. Let me remark that there are many other efficient matching algorithms, both deterministic, randomized, and parallel, but we're only focusing on the left-hand side. In this regime, the best algorithm attains a running time of n to the 5 halves, and we have the trivial lower bound of n squared, just the input size. And there's this large gap that remains unexplained. So to make matters more concrete, we're focusing on the unweighted decision variant of matching. The input is an unweighted balanced bipartite graph, and we're trying to determine whether it has a perfect matching or not. This is characterized by the following Boolean function, BPM, which receives the biadjacency matrix of the graph, that is n squared input bits, and outputs 1 if and only if it contains a perfect matching. Now, to have any computational discussion, we have to fix a computational model. We have chosen to consider the demand query model, which was introduced by Noam Nissan in a 2019 paper, and is inspired by combinatorial auctions. Before we proceed, let me just recall two quick facts that will be used throughout this talk. Firstly, any Boolean function can be uniquely represented by a multilinear polynomial over the reals. By represented, I simply mean that the function and the polynomial agree on all Boolean inputs. Secondly, let us define what's called the dual of a Boolean function. This is the function one would obtain if you negate all the input and output bits. Since this is a Boolean function, it too can be uniquely represented by a multilinear polynomial, which we call the dual polynomial. So if you were to apply this transformation to the AND function, you would obtain the OR function. So they are duals of one another. It is sometimes interesting to consider the dual polynomial, since whereas the function and its dual share many properties, their polynomial expansions can differ greatly. So back to the demand query complexity of matching. It is known that within this model, one can achieve an n to the 3 halves query complexity, for example by simulating Hophoff-Karp's algorithm. We can also relate this complexity measure to other measures, both from query and communication complexity, and algebraic measures relating to the polynomial and to its dual. The goal in constructing this diagram is to either obtain a superlinear lower bound on the demand query complexity or a new upper bound. Let me draw in green all the complexity measures for which we have a quasi-linear upper bound, either by past results or by known results. This was the state of affairs prior to this paper. Our starting point is then the following observation. Every demand query, which I have not specified in the interest of time, can be simulated by few OR queries of low arity. Since OR queries are efficiently simulated in the quantum query model by Grover's algorithm, this gives us the following relation. A good demand query algorithm implies a good quantum query algorithm, up to square root n factor. So what is known regarding the quantum query complexity of matching? On the one hand, in 2003, Zhang showed a lower bound of n to the 3 halves, using an application of Ambinus's adversary method. Conversely, in 2015, Lin and Lin constructed a quantum query algorithm of cost only n to the 7 quarters. As you can see, there's still a large gap between the two. But let me remark that any better lower bound on the quantum query complexity of matching would immediately apply a superlinear lower bound on the demand query complexity. Therefore, let us now recall the following classical result by Beals, Burman, Cleve, Mosca, and de Wolf, which is that for any total Boolean function, its quantum query complexity is lower bounded by its approximate degree, up to a constant factor. This brings us to the main object of study in this paper, the approximate degree of matching. Our main results in this paper are a tight upper and lower bound on the approximate degree of matching, up to a square root log n factor. The upper bound is shown by obtaining a complete characterization of the dual polynomial of matching, to which we apply a simple approximation scheme to obtain a low-degree approximation of the matching function. The lower bound is shown using the method of spectral sensitivity, which is a new complexity measure introduced by Aronson, Ben-David, Kotari-Rao, and Tal in a 2020 paper, which was inspired by Huang's breakthrough proof of the sensitivity conjecture. In fact, we show that this new measure is exactly n to the 3 halves for the matching function, and this gives us our lower bound. This allows us to more fully complete the picture, though the question of the demand query complexity of matching still remains open. So finally, we arrive at the approximate degree. Let me formally define what approximate degree is. So the epsilon approximate degree of a Boolean function f over n input bits is the least degree of a polynomial p that epsilon approximates f everywhere on the Boolean hypercube. In other words, it's a good L-infinity approximation of f. Usually, we're interested in the regime in which epsilon is a constant, say 1/3. So for example, if we have this Boolean function over one input bit in blue, then in red we have an epsilon approximation of it. Approximate degree turns out to be a useful complexity measure. Upper bounds on it imply algorithmic results, and lower bounds tend to imply complexity theoretic results, including the one shown on the previous slide. For a comprehensive survey, let me recommend the survey by Bunn and Thaler from last year. So let us begin with our approach for obtaining the upper bound on the approximate degree of matching. Say you have a Boolean function f written in the 0-1 basis. Then every monomial of f is, by definition, an AND function over a subset of the input bits. Now consider the following simple scheme. Simply replace every monomial with a good epsilon approximation of it for some epsilon. Of course, the errors accumulate additively, so you would need to approximate every monomial to high accuracy if you want to get a good approximation of f. But the approximate degree of the AND function is well understood by a result of Burman, Cleave, de Wolf, and Zalka, and therefore this gives us the following simple scheme for obtaining an approximation of f by approximating every monomial to sufficiently high accuracy. Let me remark that you can also use the dual polynomial to this end, since the polynomial and the dual are obtained from one another using affine transformations, which cannot increase the degree. So this gives us the following approach. If we can compute the exact polynomials for BPM and BPM star, then we can try and use them with this scheme to get a good epsilon approximation of f. In a previous paper with Noam Nissan, we obtained a complete characterization of the real multilinear polynomial representing the perfect matching function. Its monomials correspond exactly to the set of matching covered graphs, an important family of graphs that I will discuss in a moment. And the coefficient of every such graph is -1 raised to its cyclomatic number, which is the number of edges minus the number of vertices plus the number of connected components. The approach in this proof was somewhat topological, matching the monomials and coefficients of the perfect matching function to the matching covered lattice and in turn to the Birkhoff polytope. So what exactly are matching covered graphs? We say that a balanced bipartite graph is matching covered if and only if it can be written as a union of perfect matchings. If such a graph is also connected, then we call it elementary. And let me remark that elementary graphs were studied at length by Loras and Plummer and also by Hetier. So here's a schematic of a matching covered graph. We start with some perfect matching, and then we overlay another one on top of it, and another one. Let me remark that this is a simple graph, so there are no duplicate edges. On the right-hand side, we have a graph that is not matching covered, because the red edge cannot be covered by any perfect matching. The connected components of a matching covered graph, as I said, are elementary graphs, for which we use the following notation. So let me give a very brief one-slide overview of the proof regarding the perfect matching polynomial. The first step is to consider the lattice of all matching covered graphs together with the subset relation over their edges. This combinatorial lattice turns out to be intimately connected to the perfect matching polynomial. In particular, the monomials and coefficients in this polynomial correspond to the elements and Mobius numbers within the lattice, where by Mobius numbers I'm referring to the Mobius function of partially ordered sets, which is some extension of the Mobius function from number theory. The second step is to use an isomorphism theorem due to Bilera and Sangarajan, who showed that the matching covered lattice is isomorphic to the face lattice of the Birkhoff polytope. In particular, since this is a lattice that is isomorphic to the face lattice of some polytope, it is Eulerian, meaning it satisfies the Euler-Poincaré formula. Therefore, its Mobius numbers are very simple and are just given by the dimensions of every face in the lattice. So finally, it remains to compute the dimension of every face in the Birkhoff polytope. And to this end, we use the bipartite ear decomposition, which is a powerful characterization of elementary graphs due to Loras and Plummer. We show that the dimension of every such face is given by its cyclomatic number. Thinking back to our original goal, we can ask whether this polynomial representation, together with the scheme described earlier, can be used to obtain a low-degree approximation of the perfect matching function. However, this turns out not to be the case, since the support of this polynomial is too large. In fact, asymptotically almost all balanced bipartite graphs are matching covered, by a simple probabilistic method argument. Therefore, let's turn our attention back to the dual polynomial. In the same paper with Noam Nissan, we also obtained the following partial characterization of the dual. In particular, we showed that the only monomials that may appear in this polynomial correspond to the set of totally ordered graphs, which is a very sparse set. We call a graph totally ordered if, up to a permutation over its left vertices, their neighborhood sets form a chain with respect to inclusion. So for example, this graph on the left-hand side is a totally ordered graph. We also say that such a graph is sorted ordered if its bipartitions have been sorted by degrees in a non-decreasing manner, as shown on the right-hand side. Let me remark that applying this automorphism to a totally ordered graph preserves its dual coefficient, since the dual polynomial is invariant to permutations over its bipartitions. Therefore, it suffices to consider only sorted ordered graphs from here on. By construction, the biadjacency matrix of every such graph is composed by a sequence of ascending blocks, and this is the structure that we are going to analyze. For the partial characterization of the dual, obtained in the previous paper, it sufficed to take a mostly order-theoretic approach. Namely, we observed that in an Eulerian lattice, the sum of Mobius numbers in any closed non-trivial interval must vanish, and this is an immediate corollary of the Euler-Poincaré formula. To complete the characterization of the dual, the remaining work is more combinatorial. We have to understand the behavior of the biadjacency matrix of elementary sorted ordered graphs. Let me briefly sketch the proof in 3 short steps. The first step is to reduce the problem only to the permitted edges, which is a subset of the edges drawn here in green. We show that any deviation from the permitted edges, as drawn in yellow, would cause some degeneracy condition through which the dual coefficient must vanish. Secondly, we consider the growth rate of the permitted edges. We show that if they do not grow quickly enough, which we call a bad sequence, then, by relying on a theorem due to Etier, which is a characterization of elementary graphs, once again the dual coefficient must vanish. Finally, we consider the remaining sorted ordered graphs and break them into simpler blocks, drawn here in blue. Every such block is also sorted ordered and covers one block of permitted edges. Finally, we show a correspondence between the dual coefficient of the original graph and the product of dual coefficients for every such block. It then remains to handle these simple blocks, which we do directly by considering their upper sums in the matching covered lattice. Working through the details from the previous slide gives us the following characterization of the dual polynomial of matching. This resolves an open question from the previous paper. As an immediate corollary, we get the following surprising fact. This dual polynomial is both sparse, and the magnitude of its coefficients is small. In fact, they are only at most exponential in n log n. Therefore, by applying the approximation scheme we mentioned earlier, we get the following upper bound on the approximate degree of matching, which holds even for exponentially small epsilon. Now let's turn back to the lower bound on the approximate degree of matching. To present the results in the second part of this paper, let me briefly recall the notion of sensitivity. So given a Boolean function f over n input bits, we say that its sensitivity at point x is the number of indices such that if we flip the bit at that index, the value of f changes. So if you think of f as a two-coloring of the n-dimensional hypercube, its sensitivity at x is simply the number of bichromatic edges incident to x. The sensitivity of the function is then defined to be the maximum over all x's. Now let me define the sensitivity graph. So given a Boolean function, we can think of the sensitivity graph as the f-cut of the hypercube. Or in other words, we take the bipartite graph whose left vertices are the 0 inputs, right vertices are the 1 inputs, and we join them by an edge if and only if they differ in Hamming weight exactly by 1. So this bipartite graph can easily allow us to read off the sensitivity, since the sensitivity of f is simply the maximum degree in this graph. In a 2019 paper, Huang gave a very elegant proof of the sensitivity conjecture, showing that for any total Boolean function, its degree is bounded by, at most, its sensitivity squared. In fact, the proof is so elegant that it fits in a tweet. Later, in 2020, Aronson, Ben David, Kotari, Rao, and Tal noticed that at the heart of Huang's proof lies a new complexity measure, spectral sensitivity, which we now define. So the spectral sensitivity of a Boolean function is the spectral radius of its sensitivity graph, which I remind you is the f-cut of the hypercube. By spectral radius, I am referring to the largest eigenvalue in magnitude of the adjacency matrix. But remember that since this is a bipartite graph, its spectrum is symmetric, so this is simply the top eigenvalue. In the same paper, they proved the following two results. First, as a reinterpretation of Huang's result, they show that for any total Boolean function, the degree is bounded by, at most, the spectral sensitivity squared. Secondly, they show that the approximate degree of any Boolean function is lower bounded, up to a constant factor, by its spectral sensitivity. Notice that this is a new lower bound technique for approximate degree, and whereas known techniques do not seem easily applicable to the perfect matching function, this technique might be so. Let's take a moment to think about the sensitivity graph of the matching function. In our case, every input is associated with some subgraph of the complete bipartite graph. And an input is a 1 input if it contains a perfect matching, and 0 otherwise. In other words, we have a bipartite graph in which every vertex is itself a bipartite graph, and we join every two such graphs if they differ by a single edge. And on the left-hand side, we have graphs that do not contain a perfect matching, and on the right-hand side, we have graphs that do contain a perfect matching. Notice that since the perfect matching function is monotone, we can only add an edge going from left to right and remove a single edge going from right to left. In the interest of time, let me just show the lower bound on the spectral sensitivity of matching. But I remark that showing the upper bound is relatively straightforward. In fact, it follows from the Hölder inequality for matrix norms, and by giving an upper bound on the left and right degrees in the sensitivity graph. As for the lower bound, we claim that it suffices to exhibit some induced subgraph of the sensitivity graph that has high enough spectral radius. This follows by Cauchy's interlace theorem in the following way. Taking an induced subgraph means that the top eigenvalue cannot increase. However, since both of these graphs are bipartite, their spectrum is symmetric, and therefore this implies that nor can the spectral radius increase. Finally, in the next slide, we'll construct such a biregular induced subgraph with left degrees n squared and right degrees roughly n. And this suffices, since for any biregular graph, it is not hard to show that the spectral radius is exactly the geometric mean of the left and right degrees. In fact, you can do that by constructing the eigenfunction that places an appropriate weight on the left and right bipartition. Our construction is as follows. Let A, the set of left vertices, be partitioned into A1 and A2. And similarly, let B, the set of right vertices, be partitioned into B1 and B2, where A1 and B1 are of cardinality k, and A2 and B2 are of cardinality n minus k. Now, for our set of left vertices, that is 0 inputs, we're going to take all the graphs that are built in the following way. They have a biclique between A1 and B2, and a biclique between A2 and B1, so we fix all the edges there, and then we also add a matching of size n minus 2k minus 1 between B2 and A2. Notice that these graphs do not contain a perfect matching, since, for example, the set B2 violates Hall's condition. It has fewer neighbors than its cardinality. As for our right vertices, that is 1 inputs, we're going to take all the graphs that are exactly the same, but now the matching in the middle is of size n minus 2k. And these graphs do contain a perfect matching, since once you take the matching in the middle, you're left with k vertices in B2 and A2, and you can match those with the biclique to A1 and B1. It remains to compute the degrees in this graph. So how can you get from a 0 input to a 1 input? Well, you pick any two free vertices in B2 and A2 and join them by an edge. And there's exactly k plus 1 squared ways to do that. And going from right to left, you pick one of the matching edges and you remove it, of which there are exactly n minus 2k. The proof now follows by taking k to be linear in n, say n over 3. Using the two theorems that we have just shown allows us to give a tight bound both on the spectral sensitivity of matching and on its approximate degree. We remark that all of our results appear consistent with the existence of a quasi-linear algorithm for matching. However, we are still unable to show the existence of one, nor are we able to give a superlinear lower bound on, say, the demand query complexity of matching. To wrap things up, let me mention two open questions which I find very interesting. Firstly, I would like to suggest that the sparsity and low magnitude of the dual polynomial, in other words, its one norm, can be used to obtain further algorithmic results. For example, it's not hard to show that for any monotone Boolean function, the deterministic communication complexity is at most the square of the logarithm of the one norm of its representing polynomial. In fact, I conjecture the following stronger claim holds, that one can compute any Boolean function f using a decision tree of depth proportional to the logarithm of its one norm, in which every internal node corresponds to an AND over a subset of the input bits. We call such a tree an AND decision tree. Since every AND gadget can be solved using at most 2 bits of communication, this also clearly gives an efficient deterministic communication protocol. In a 2020 paper, Knopp, Lovett, Maguire, and Yuan showed a similar bound, but with a 5th power separation, whereas we conjecture it can be lowered to 1. We do not yet know of any counterexample for this claim. Secondly, it would be interesting to complete the bound on the quantum query complexity of matching, but, as we have shown, the polynomial method cannot be used to this end. That's it. For more details, I encourage you to read the full paper, and thank you very much for listening.